Okay, thanks for joining me. Today we're going to look at a fairly basic mathematical concept, that of continuity. It turns out that we do need some fairly technical mathematical notation to formally define what it means for a function to be continuous at a point. So we are going to work that out as we look at and compare some different graphs that you see on the screen. So join me in just a simple thought about the, let's not overcomplicate it. Let's just think about what does it mean to you if I say, if I ask the question, for which graph is the function continuous at x equals 3? So just pause and think about that. No technicalities here. Which one would you say is continuous? Good. So hopefully you said C is the continuous one, the only continuous one of the four graphs that I have on the screen. And I would say what I'm using right now for my definition, if you will, of continuity, my concept is I can draw the whole graph without picking up my pencil. That's it. Here I need to somehow skip over a point, so that does require picking up my pencil. Here I have to skip over but jump down here to then define the point in a different spot and then keep going, and then here I actually have to jump to a different spot to continue making my graph. So C is the one that's continuous, so we are going to keep that in mind. We're going to look at kind of approaches from the standpoint of what's different about these graphs. What can we say that we know to be true at x equals 3 in each of these examples, and by the end we will figure out what actually makes C officially continuous. How do I state that in precise mathematical language? So let's go back to pre-calculus, prior to calculus, really algebra 1 here, of talking about at x equals 3. Maybe we are to start with A because it's not true, so let's jump over to B. At x equals 3, if I talk about the functional value, the point on the graph f of 3 does equal 1 in B. I'm talking about that point. Jumping to C, f of 3 equals 2 in that case, so I have a point on the graph. And in D, f of 3 equals 1. I've got a point. So now let's go back to A, and f of 3 does not exist or is undefined. There is no point. That is going to be problematic when we talk about continuity. So we will come back to A sort of is one example of how we can fail, a function can fail to be continuous if it's not defined at a point. But then let's talk about B and D have something else going on because they are clearly defined, but we already agreed C was the only continuous graph. So this takes us into the world of calculus and notation that we've been practicing with. Let's talk about limits. And just kind of go through each one here. Limit as x approaches 3 of f of x in A. Limit is all about what I'm approaching from the left and the right. I'm approaching the same value, and that is 2. So even though it's not defined, I do have a limit there. This is a good review of our limit, graphical limits, which we have not spent a ton of time with. In letter B, limit as x approaches 3 of f of x. Well, I basically have the same thing going on as A. Ignore that point, and that part of the graph looks the exact same. We still have a limit of 2. Left and right hand limits are equal to each other. We have the same thing going on here. I'm not paying attention to that green point. I'm just looking at what's happening around that point. From both sides, I am approaching the same value of 2. So in this one, D, or in this particular discussion, D is the one that's different. What would you say about the limit as x approaches 3 in D? And hopefully you're saying the limit does not exist, because here's what's happening. From the left-hand side, I'm going towards 2. So that left-hand limit, let me make that a little bit clearer. That left-hand limit is 2. But the right-hand limit is 1. So if those don't equal to each other, we know this fact. If those don't equal to each other, then I do not have a two-sided limit. So there's an implied thing that we need to consider here, which is in order to state that the limit exists, we need to check the left and the right hand limits. So there we have kind of our analysis of what is going on each of these graphs. So let's go back to that question of what makes a function continuous, so we can get a formal definition here on our papers. Like I said, we've got this in A, we've got this does not exist, the value doesn't exist, the function is not defined at x equals 3. And if either of these first two conditions, if you will, fails, that is a case of discontinuity. The system breaks down. So we've got the same thing happening here, this does not exist. But B, I think, is a very interesting case because B, so far, looks very similar to C. We have a value and we have a limit. So if C is the only continuous one, what's the difference here? And I know that you guys are observant mathematicians and you're noticing, oh wait, we've got two different answers, two different y values for our functional value and our limit, and conceptually that is causing a break in discontinuity. Those do need to be the same. So even though both conditions are met, we have a case in B of f of 3 is not equal to the limit as x approaches 3. Therefore, f of x is not continuous. At x equals 3 versus in C, we have f of 3 is equal to the limit as x approaches 3. Those are the same value, therefore, f of x is continuous at x equals 3. So let's just kind of define in abstract terms. We'll change our 3 to a random x value. Let's call it a, and let's get this down in our notes. So if you didn't write that stuff down, please join me in writing this down. This is the three-part definition of continuity that I am going to refer back to many times. And you will be responsible for using and writing out good notation. A function is continuous at an interior point x equals a if and only if the following three things hold true. I'll go in the same order. There's really no specific order to 1 and 2. They can be reversed, but just to be consistent. Feel free to annotate your notes. F of a exists. That means that there is a value. There is a point. So A was the one where that failed. The limit as x approaches a of f of x exists. So this was the one where D failed. So D is a case of 1 is true, but 2 is not. A is a case of 1 is not true, even though 2 is. There's an implied question here, and let's put this down. Limit as x approaches a from the left equals limit as x approaches a from the right. You will need to prompt yourself to think about that, as I've been telling you all along. In order to say the limit exists, we need to check the left and the right hand limits. And finally, the functional value is equal to the limit as x approaches a of f of x, because as we saw in our lovely graph B, we have a limit and a functional value, but they are not equal to each other. Okay, not trying to overcomplicate something that is simple, but there's a lot of math notation going on here, so we do kind of have to talk ourselves through it. Make sure you've got that down in your notes, and then we're going to do one more quick bit of notes here. Okay, so types of discontinuities. This is just a classification thing, and these words will come up. We've actually already used some. We've talked about some of these. So I just wanted to do a quick sorting out. This isn't a huge deal. It's not something we'll use a ton, but it does sometimes show up on the AP exam, so it is something that I don't want to skip over and just assume that you know. So we have removable and non-removable discontinuities. The only type of removable discontinuity that I'm aware of is the whole. And the way that this is described is you can fix it. So if you want to make a note to yourself, you can fix a removable discontinuity. You can remove the discontinuity by simply redefining or defining the function at a particular point. So if we go back to our graph A on the previous screen, we could fix that discontinuity by simply defining f of 3 equals 2 and giving it a value. We could have, if there's a hole and then a point and another point, we can redefine it and make them the same. So kind of speaks for itself. Non-removable discontinuities, we have 3 types of those. So the most common is the jump discontinuity. So that is what we saw in our graph D, where the left-hand limit is not equal to the right-hand limit. Another way of saying that is to say that the limit doesn't exist. Then we've got our infinite discontinuity. I don't know if I've used this word or term. Those are your vertical asymptotes going to infinity. And then finally we have our oscillating discontinuity. We use this to describe, we use the term oscillating to describe a limit, when a limit not existing as we go towards infinity with one of our sinusoidal functions like sine of x. This is a little bit different because we're talking about a specific point, not as x is going towards infinity. But there are some functions that as you zoom in really close to a point, they keep oscillating and never actually reach a value. Very weird. You probably haven't really looked at any of these. So I would encourage you to open up a Desmos tab. Is probably going to be the easiest way to zoom in and take a look at the function y equals sine of 1 over x or y equals cosine of pi over x would be a couple to look at. I can't switch on my screen right now. I can't switch, I don't think, and go to Desmos. So explore that, and we can talk about that more if you have questions. Otherwise, those are your types of discontinuities, so you got a nice list to go back to as needed.